The ocean has never struggled to create an apex predator. What it has never done is keep one forever. Across more than 500 million years of Earth's history, the seas have repeatedly produced hunters so successful that they seemed impossible to replace. They ruled entire oceans, shaped marine ecosystems on a global scale, and survived for spans of time that dwarf the existence of our own species. Every one of them disappeared. The plesiosaurs remained among the ocean's dominant predators for more than 100 million years, armed with jaws reaching 2 meters in length, that is about 6.5 feet, and a bite capable of crushing bone with astonishing force. Ichthyosaurs mastered open water so completely that their bodies evolved into one of the most efficient swimming designs nature has ever produced. They ruled the seas for 157 million years before vanishing without a single descendant. Then came Megalodon, the largest predatory fish known to science. Growing to nearly 18 meters in length, that is about 59 feet, it spent 20 million years at the top of the marine food chain before disappearing approximately 3,600,000 years ago. None of these dynasties ended because another predator proved stronger. The rocks tell a different story. Again and again, the ocean itself changed in ways that made their survival impossible. Sometimes the change began with volcanoes, sometimes with the chemistry of seawater, sometimes with the slow movement of continents. Each time, the result was the same. The ruler of the ocean became another fossil. In tonight's journey, we're tracing the remarkable pattern hidden across hundreds of millions of years, one that connects every vanished giant that oceans have ever produced. If these quiet journeys through Earth's history are something you enjoy, consider giving this video a like and subscribing. It helps this channel reach more people who enjoy exploring the natural world at a slower pace. Now, let's begin in an ocean that built extraordinary predators, only to erase them time and time again, long before any giant predator could patrol the prehistoric seas. The ocean first had to become an environment capable of sustaining such immense lives. Great hunters were never created in isolation. They emerged only after countless smaller relationships had settled into balance, each one supporting the next until an entire living structure reached upward through the water. At its highest point stood the apex predator, but beneath that commanding presence stretched an intricate foundation built over immense spans of geological time. Every powerful marine hunter depended upon a food chain composed of many connected layers. Large predators required abundant prey. Those prey animals relied upon immense schools of smaller fish. The smaller fish depended upon microscopic phytoplankton drifting through the sunlit surface waters. Those tiny organisms, although nearly invisible, transformed sunlight and dissolved nutrients into the energy that sustained almost every larger creature in the sea. Remove even one layer from this arrangement, and the entire structure weakened from its base upward. Those productive blooms did not appear by chance. They depended upon a remarkable planetary system known as thermohaline circulation, the global movement of deep ocean water driven by differences in both temperature and salt content. Cold, dense water sank into the depths, while warmer water remained nearer the surface. Across thousands of years, these enormous currents carried oxygen downward and lifted nutrient-rich water back toward the light. When those nutrients reached the upper ocean, phytoplankton flourished, and the foundation of the marine food web renewed itself again and again. During many chapters of Earth's ancient history, this system operated beneath oceans that differed greatly from those of the present day. Sea levels often stood much higher, flooding continental margins beneath broad expanses of shallow water. These warm inland seas formed environments where sunlight easily reached the seafloor, encouraging extraordinary biological productivity. Vast coastal habitats became feeding grounds for fish, marine reptiles, mollusks, and countless smaller organisms, creating a continuous supply of prey capable of sustaining animals of astonishing size. These shallow environments also served another purpose. Protected waters offered places where young predators could mature before entering the dangers of the open ocean. Instead of growing within isolated pockets, entire generations developed alongside dense populations of prey, allowing even enormous species to complete life cycles that stretched across many years. Stability, rather than abundance alone, made these ecosystems capable of supporting giants. The predators themselves reflected that stability. A massive hunter consumed extraordinary amounts of energy every day, and such demands could only be met by an ocean whose productivity rarely faltered. Yet these same animals reproduced slowly. They reached maturity after long periods of growth, produced relatively few offspring, and invested heavily in each new generation. Their populations expanded gradually, balancing themselves against the resources available around them. This slow rhythm allowed apex predators to remain dominant for millions of years whenever environmental conditions remained favorable. Such biological strategies carried an unseen cost. Because populations renewed themselves so gradually, even modest disruptions required immense spans of time to repair. A decline in prey echoed through every level above it. Reduced plankton growth eventually meant fewer small fish, then fewer larger hunters, until the greatest predators found themselves supported by a narrowing foundation. Their strength depended less upon their own size than upon the uninterrupted health of every living layer beneath them. Viewed across geological time, the prehistoric ocean appears almost like a vast engine whose moving parts remained carefully connected. Chemistry, circulation, sunlight, nutrients, and life worked together in patterns that could endure for millions of years while never becoming permanent. The giants that eventually emerged were not inevitable achievements of evolution, but expressions of conditions that happened to align with remarkable precision. When those conditions endured, the ocean produced some of the most formidable predators Earth has ever known. When those conditions shifted, even slightly at first, the immense biological architecture that sustained them became vulnerable long before the predators themselves revealed any sign of decline. Far from the ancient shorelines where giant hunters pursued their prey, another process unfolded beneath continents that appeared motionless from the surface. Deep within the planet, heat gathered over spans of time so immense that entire biological dynasties could rise and flourish before the pressure found release. When it finally did, the consequences extended well beyond the land, reaching oceans that might have seemed untouched by events unfolding far inland. Among the greatest expressions of this internal energy are formations known as large igneous provinces. These are vast regions where material rising from Earth's mantle pours extraordinary volumes of basaltic lava across the surface, over periods lasting from tens of thousands to millions of years. They are not single volcanoes, but prolonged episodes of planetary outpouring, capable of covering landscapes with successive layers of molten rock until entire regions are transformed. Throughout the geological record, these immense volcanic episodes appear again and again beside some of the most significant marine extinction events ever documented. The most carefully studied example is the Siberian Traps, whose eruptions began about 252 million years ago. Over roughly 1 million years, these eruptions released extraordinary quantities of carbon dioxide into the atmosphere. Unlike the brief violence often associated with volcanic explosions, This process unfolded through relentless persistence. Layer after layer of lava emerged while gases accumulated above the planet, gradually altering the chemistry of the atmosphere itself. The transformation did not happen within a single lifetime. It unfolded across generations beyond counting, until the balance that had sustained ancient oceans began to shift. An even earlier example lies within the Villi Traps of Siberia, which erupted around 374 million years ago, only a relatively brief geological interval before the Kellwasser extinction. Together, these eruptions produced approximately 240,000 cubic miles of lava, an amount difficult to picture even across modern landscapes. Their importance lies not merely in the volume of rock produced, but in the prolonged release of volcanic gases that accompanied the eruptions. Those gases slowly accumulated until their influence extended across the atmosphere and into the sea. Carbon dioxide acts as a blanket around the planet, reducing the escape of heat into space. As atmospheric concentrations increased, the ocean surface gradually warmed. Warmer surface water became less willing to sink into the depths, weakening the great circulation systems that normally carried oxygen downward while returning nutrient-rich waters toward the light. As this circulation slowed, deep water remained isolated for longer periods, and the chemical character of the ocean began changing from the depths upward. What had once been an interconnected system slowly separated into layers that exchanged less oxygen and fewer nutrients. Volcanic eruptions also released enormous clouds of ash capable of reducing incoming sunlight for limited periods, producing intervals of temporary cooling, often called volcanic winters. Yet these episodes represented only a passing chapter within a much longer story. The ash eventually settled back to Earth, while the accumulated carbon dioxide remained in the atmosphere, continuing to influence climate across thousands and even hundreds of thousands of years. The sustained warming produced by those gases became the dominant force shaping marine environments, gradually outweighing the shorter cooling intervals that preceded it. This gradual pace is one of the defining features of geological catastrophe. Oceans do not transform overnight, nor do ecosystems collapse in a single season. Instead, physical and chemical changes accumulate with remarkable patience. Water temperatures shift little by little. Ocean circulation weakens almost imperceptibly. Oxygen distribution slowly changes. Living communities continue adapting until the balance supporting them grows increasingly narrow. By the time the largest predators begin to experience the consequences, the processes responsible have already been unfolding beneath continents and across the atmosphere for spans of time so vast that no individual organism could ever perceive the beginning of the transformation. The first signs of collapse did not appear in the jaws of the largest hunters or in the disappearance of giant prey. They emerged in the chemistry of seawater itself, where one of the most fundamental requirements for complex life slowly diminished. Ocean anoxia is the name given to this condition. It describes an ocean that has lost so much dissolved oxygen that large regions can no longer support the animals that once thrived there. The change begins invisibly, yet its influence spreads through every layer of the marine world. The process follows principles that govern water everywhere on Earth. Cold water can hold more dissolved oxygen than warm water. As volcanic warming gradually raised ocean temperatures, the amount of oxygen available to marine organisms naturally declined. This reduction did not happen evenly across every depth. Surface waters remained connected to the atmosphere, where oxygen could still dissolve into the sea. The deeper waters depended upon the great circulation systems that carried freshly oxygenated water downward while returning older water toward the surface. When those currents weakened, the deep ocean became increasingly isolated. Water that should have mixed across immense distances remained trapped beneath warmer layers above. Organic material drifting downward from the productive upper ocean continued to settle through the water column, where bacteria broke it apart as part of the ordinary cycle of decomposition. Those microscopic organisms consumed dissolved oxygen throughout the process. Under normal conditions, circulation continually replaced what they used. Without that renewal, oxygen reserves steadily diminished until broad regions of the deep ocean became incapable of sustaining much complex life. The destructive power of ocean anoxia did not lie in sudden suffocation of the largest predators. Instead, it unraveled the living network from its foundation upward. Plankton communities changed as nutrient cycles shifted. Small animals that depended upon oxygen-rich habitats declined or retreated into shrinking refuges. Fish populations followed as food became less dependable and habitable waters contracted. Each layer of the food web carried the effects upward until the greatest hunters found themselves supported by an ecosystem that could no longer provide enough energy to sustain them. Their decline reflected the disappearance of everything beneath them rather than a direct encounter with hostile water. This sequence has been reconstructed through remarkably detailed evidence preserved inside ancient rocks. Geologists examine geochemical indicators, including uranium isotopes, sulfur isotopes, and concentrations of the element molybdenum locked within marine sediments. These chemical signatures record the oxygen conditions that existed when the sediments were deposited upon the seafloor. Across the boundaries marking Earth's major marine extinction events, these records repeatedly reveal widespread oxygen depletion. Long after the vanished oceans themselves disappeared, their chemistry remained preserved as an enduring archive beneath layers of stone. Additional support emerged through the work of Professor Maya Elric at the University of New Mexico while studying marine limestone deposited during the late Ordovician. Her research identified what she described as the first evidence for abrupt global ocean anoxia, beginning and continuing through both the peak and the decline of glacial conditions. The finding demonstrated that depleted ocean oxygen was not confined to a single extinction event or one unusual period in Earth's history. Instead, it appeared as a recurring process capable of crossing very different climatic states while producing remarkably similar biological consequences. For apex predators, this pattern revealed an extraordinary vulnerability hidden beneath apparent dominance. Every successful hunt depended upon prey populations that themselves relied upon countless smaller organisms, stretching back to microscopic producers near the ocean surface. No predator, regardless of strength or size, could separate itself from that chain. Ocean anoxia severed its earliest links with patient consistency. By the time shortages reached the largest hunters, the damage had already spread through every supporting layer of the ecosystem. The disappearance of the giants, therefore, began not with their own failure, but with the gradual exhaustion of the living foundation upon which their existence had always depended. Long before marine reptiles and giant sharks inherited the role of supreme hunters, another dynasty ruled the seas beneath forests that had only recently begun spreading across the continents. The late Devonian Ocean was filled with sprawling reef systems unlike any that exist today, where intricate communities of corals, shell-bearing animals, fish, and countless smaller organisms formed one of the richest marine ecosystems in Earth's history. Among the dominant predators were the armored placoderm fishes, including Dunkleosteus, whose immense jaws stood at the summit of a food web that had taken millions of years to assemble. The beginning of its decline can now be placed with remarkable precision. Layers of volcanic ash preserved within ancient rock contain tiny zircon crystals that record the passage of geological time through uranium-lead dating. These crystals indicate that the Kellwasser event occurred approximately 371.87 million years ago, with an uncertainty of only about 1/10 of a million years. Such precision allows scientists to compare biological change with environmental change in extraordinary detail, revealing that the disappearance of these predator communities unfolded alongside profound transformations in the ocean itself. No single cause acted alone. Vast volcanic eruptions associated with large igneous provinces released carbon dioxide into the atmosphere across immense spans of time, gradually altering global climate and ocean circulation. At the same time, the continents were changing in another remarkable way. Early forests expanded across broad landscapes, anchoring themselves with increasingly complex root systems. Those roots accelerated the breakdown of exposed rock, releasing nutrients that rivers carried toward the sea. Fertile coastal waters responded with enormous blooms of phytoplankton, whose abundance briefly increased biological productivity before creating an unexpected consequence. As those microscopic organisms completed their life cycles, countless remains drifted into deeper waters. There, bacteria decomposed the sinking organic material, steadily consuming dissolved oxygen. Combined with weakened circulation caused by climatic warming and changing ocean structure, this process expanded broad regions where oxygen became increasingly scarce. Astronomical forcing added another layer to the transformation. Gradual variations in Earth's orbit and axial orientation altered patterns of solar energy reaching the planet, reinforcing intervals of cooling and strengthening the environmental instability already spreading through marine ecosystems. Each influence alone might have produced only regional disruption, yet together they reshaped the chemistry of entire ocean basins. The fossil record preserves this transformation with striking clarity. Between roughly 70 and 82% of all known species disappeared during the Kellwasser crisis, with marine organisms suffering the greatest losses. Layers of dark black shale deposited across many ancient seafloors reveal waters that had become euxinic, containing little or no oxygen while also accumulating hydrogen sulfide. These rocks are more than sediment. They are chemical archives, preserving the conditions under which thriving ecosystems gradually lost the environmental balance that had sustained them for millions of years. Even then, the story did not end with a single extinction pulse. Near the close of the Devonian period, around 359 million years ago, another crisis known as the Hangenberg event swept through the oceans. Predator communities that had survived the earlier collapse encountered another period of severe environmental disruption. This second wave completed the disappearance of the armored placoderms, ending one of the longest-lasting predator dynasties the marine world had ever produced. Their absence marked not simply the loss of remarkable animals, but the conclusion of an evolutionary chapter that had endured across vast stretches of geological history. The Devonian record offers an important perspective on how apex predators disappear. Ocean anoxia did not need to spread through every corner of the sea to bring about their decline. It only needed to weaken enough of the interconnected food web that supported them. As productive habitats contracted and prey became less abundant, the immense energy demands of the largest hunters could no longer be sustained. Their extinction emerged from the gradual unraveling of countless smaller lives beneath them, each loss reducing the strength of the living foundation until even the mightiest predators could no longer endure. There are moments in Earth's history when the scale of change becomes almost impossible to compare with anything that came before or after. The boundary between the Permian and Triassic periods marks one of those moments. Around 252 million years ago, the oceans entered the greatest biological crisis ever recorded, a transformation so complete that it reshaped the future of complex life itself. Every extinction discussed before this point revealed part of the pattern. Here, the pattern reached its most extreme expression. The driving force once again rose from deep within the planet. Across what is now Siberia, the Siberian traps erupted over a period of roughly 1 million years, releasing extraordinary amounts of carbon dioxide into the atmosphere. These eruptions covered immense regions with successive lava flows while continuously altering the chemistry of the air above. As atmospheric carbon dioxide accumulated, global temperatures climbed, and the oceans absorbed both heat and changing chemical conditions. The consequences spread through the sea with relentless patience, altering circulation, reducing oxygen, and placing increasing pressure upon every level of marine life. Climate models, supported by geochemical evidence preserved within ancient sediments, indicate that the oceans lost approximately 76% of their dissolved oxygen during this crisis. No other known event in the fossil record approaches such an extensive reduction. Waters that had once circulated through deep basins became increasingly stagnant, while oxygen-rich habitats contracted toward the surface and into scattered refuges. Vast portions of the marine environment no longer possessed the chemical conditions required to sustain the diverse communities that had flourished for millions of years. The extinction itself unfolded in two major pulses across approximately 55,000 years. The first arrived as environmental systems became increasingly unstable. Species that depended upon narrow ecological conditions began disappearing as warming, declining oxygen, and disrupted nutrient cycles intensified together. The second pulse occurred after these stresses reached their greatest severity, completing a biological collapse that extended through nearly every marine ecosystem. To any individual organism, these changes would have unfolded across countless generations, each inheriting a world slightly different from the one before. By the end of the crisis, approximately 96% of all marine species had vanished. The losses extended far beyond the largest predators. Coral communities disappeared across enormous regions. Brachiopods, bryozoans, and many shell-bearing animals that had formed essential components of ancient ecosystems declined catastrophically. Equally significant was the devastation among planktonic organisms drifting through the upper ocean. These microscopic communities formed the foundation upon which every larger animal ultimately depended. Once their diversity collapsed, the entire marine food web lost its structural support. The character of the ocean also changed in a more fundamental way. Eukaryotic algae, whose productivity had sustained complex food chains, gave way across many regions to communities dominated by nitrogen-fixing bacteria and green sulfur bacteria, organisms better suited to oxygen-poor conditions. This shift represented far more than a change in species composition. It reflected a transformation in the basic functioning of marine ecosystems. The biological engine that had powered rich and interconnected food webs was replaced by communities adapted to a world with profoundly different chemistry. Among the earliest casualties were the tectonic animals, the free-swimming predators that occupied the highest positions within marine food chains. Their immense energy requirements could no longer be supported as prey communities unraveled beneath them. Meanwhile, many bottom-dwelling organisms faced an equally prolonged struggle. Recovery of benthic ecosystems unfolded so slowly that meaningful restoration extended across much of the Triassic period, requiring tens of millions of years before diverse communities again became established. When life gradually expanded into the oceans once more, it did not rebuild the Permian world. The extinction had erased too much of the previous biological architecture. New food webs emerged from different survivors, different ecological relationships, and different evolutionary opportunities. The sea that followed was connected to the one that came before by continuity of water alone. Its living communities, its dominant organisms, and the pathways through which energy moved had all been fundamentally transformed, revealing that even the greatest marine ecosystems can be rewritten when the chemistry of the ocean itself crosses its most critical thresholds. Temperature is often described as a number, a simple measurement recorded in water or air. Across geological time, however, it has acted as something far more profound. It has shaped the architecture of entire oceans, determining where nutrients travel, where oxygen remains abundant, and which animals can successfully complete their lives. Long before any predator encountered changing prey or unfamiliar competitors, temperature had already begun deciding whether the ecosystem supporting that predator could continue to exist. The relationship begins with a basic property of seawater. Cold water holds more dissolved oxygen than warm water. As surface waters cool, they become denser and sink toward the depths, carrying oxygen with them. This descending movement helps power the immense circulation systems that connect the upper and lower ocean. At the same time, deeper water, rich in nutrients, gradually rises toward the sunlight, where microscopic plankton transform those nutrients into living matter. The richest feeding grounds in any ocean emerge where this upward movement, known as upwelling, continually renews the surface with fresh nutrients from below. These productive regions support vast schools of fish, marine mammals, and eventually the great predators that depend upon them. When ocean temperatures shift, this entire system begins changing with them. Warmer surface water becomes lighter and resists sinking, reducing the exchange between shallow and deep layers. Less oxygen reaches the depths, while fewer nutrients return upward to nourish plankton communities. The effects spread gradually through the food web, influencing organisms that may never encounter the changing water directly. A predator hunting near the surface depends just as completely upon these deep currents as the smallest drifting plankton, because both are connected through the same chain of biological productivity. Different apex predators evolved within different thermal worlds. Megalodon flourished in warm, shallow seas, where abundant marine mammals occupied tropical and subtropical coastlines. Its physiology, hunting strategy, and distribution reflected those conditions. As global temperatures shifted and warm habitats contracted, the environments capable of supporting such a giant also became smaller. Productive feeding grounds moved toward cooler waters beyond the range where Megalodon functioned most effectively. The challenge was not simply warmer or colder water. It was the disappearance of the environmental conditions upon which an entire way of life depended. Other predators experienced the opposite transformation. Pliosaurs, during several intervals of their long history, occupied cooler, oxygen-rich marine environments supported by vigorous circulation. They were not overcome by advancing cold. Instead, periods of intense global warming reduced dissolved oxygen and disrupted the circulation patterns that sustained the prey communities beneath them. The same physical process that favored one ecosystem during one era became destructive when carried beyond critical limits. Temperature itself did not select winners or losers. It altered the framework within which survival became possible. These changes unfolded across more than one rhythm. Some occurred gradually through the slow movement of continents and the subtle variations of Earth's orbit around the Sunday. Across millions of years, oceans warmed or cooled as geography and climate slowly evolved, allowing many species enough time to shift their ranges or adapt through successive generations. Other changes arrived far more rapidly. Immense volcanic episodes released vast quantities of carbon dioxide, producing comparatively swift warming that outpaced the ability of slow reproducing predators to respond. Ecosystems that had remained stable across immense stretches of time entered periods of rapid adjustment for which many specialized animals possessed little resilience. The fossil record reveals that these transitions rarely progressed in a smooth, predictable fashion. Marine ecosystems often tolerated gradual warming until critical thresholds were crossed, after which biological communities reorganized with surprising speed in geological terms. Food webs that had appeared remarkably stable for millions of years gave way within comparatively brief intervals, not because temperature alone destroyed them, but because warming altered oxygen, circulation, nutrient delivery, and countless ecological relationships simultaneously. In this way, temperature became less a solitary cause than a governing force, setting in motion a sequence of chemical and biological changes that together reshaped the living ocean. Across the immense span of the Cretaceous period, there came an interval when the oceans reached a remarkable state of warmth, one that reshaped marine life on a global scale. Near the boundary between the Cenomanian and Turonian ages, approximately 93.5 million years ago, the planet entered what is known as Oceanic Anoxic Event 2. Rather than removing a single dominant species, this event transformed entire communities of apex predators, providing one of the clearest demonstrations that changes in ocean temperature and chemistry could erase even the longest enduring marine dynasties. During this interval, atmospheric carbon dioxide reached some of its highest known levels of the Cretaceous period. As the atmosphere retained more heat, ocean temperatures rose across vast regions of the world. The warming did more than alter climate. It weakened circulation, reduced the movement of oxygen into deeper waters, and disrupted the steady exchange of nutrients that had sustained productive marine ecosystems for millions of years. The living structure supporting the greatest hunters became increasingly unstable, even while the predators themselves continued to occupy the summit of their food webs. For generations beyond counting, pliosaurs had stood among the most formidable hunters ever to inhabit the sea. Some possessed jaws measuring as much as 2 meters, which is about 7 feet, lined with massive teeth capable of crushing bone and seizing enormous prey. Since the early Jurassic period, they had ruled alongside ichthyosaurs, whose streamlined bodies represented one of the most efficient designs ever produced by marine evolution. Along coastlines and farther offshore, the Latitusian crocodiliforms occupied additional hunting niches, creating an ocean shared by several powerful predator lineages that had persisted across more than 100 million years of changing environments. Then the fossil record records an unusually compressed transition. Geological layers deposited during Oceanic Anoxic Event 2 reveal that ichthyosaurs disappeared from the record. The Thalattosuchian crocodiliforms also vanished, while the great pliosaurs followed them into extinction. These losses occurred within the same broad interval, not as isolated events separated by vast spans of time, but as parts of a larger biological reorganization affecting marine ecosystems across much of the globe. Research presented during the year 2025 at the European Geosciences Union General Assembly offered additional insight into the mechanisms behind this transformation. Evidence pointed toward a combination of widespread ocean anoxia and climatic instability rather than a single environmental disturbance. Changes in ocean chemistry, including shifts involving sulfur and iron, altered the cycling of nutrients that sustained plankton communities. As those microscopic foundations changed, the productivity supporting fish populations and larger prey also shifted. The disappearance of apex predators reflected this gradual restructuring from the lowest biological levels upward, rather than direct competition with stronger hunters. The oceans did not remain empty after these ancient rulers vanished. Evolution responded by filling newly available ecological space with different lineages shaped for the altered world. Mosasaurs expanded rapidly in both diversity and body size, becoming the dominant marine reptiles of the late Cretaceous. Long-necked plesiosaurs broadened their ecological presence, while shark lineages diversified into forms that occupied a growing range of habitats and feeding strategies. The transformation did not restore the previous balance. It established an entirely different one, built upon survivors whose biological traits better matched the new chemical and thermal conditions of the sea. Oceanic Anoxic Event 2 reveals that longevity alone offers no guarantee of permanence. Predator lineages capable of dominating oceans for more than 100 million years remained dependent upon environmental conditions extending far beyond their own biology. Once warming, declining oxygen, disrupted nutrient cycles, and changing chemistry crossed critical thresholds together. Even these extraordinarily successful hunters could not preserve their place within the marine world. Their disappearance stands as one of the clearest examples in the fossil record that the greatest predators are ultimately governed by the changing systems beneath them, systems that continue evolving according to the rhythms of the planet itself. An ocean can appear full of life while already carrying the conditions for decline. The disappearance of an apex predator does not always begin with changing chemistry or diminishing oxygen. Sometimes the decisive change unfolds among the countless animals that exist beneath it, where the gradual loss of prey quietly transforms abundance into scarcity. In these moments, the predator itself may remain healthy for generations, even as the biological foundation supporting its existence steadily contracts. Every apex hunter occupies the highest point of a food chain built from many interconnected layers. Large predators depend upon substantial populations of medium-sized prey. Those animals rely upon even smaller fish and invertebrates, which themselves depend upon plankton nourished by sunlight and nutrients. The energy flowing upward through this structure diminishes at every step. By the time it reaches the largest hunters, only a small fraction of the original productivity remains. Even a modest reduction near the base becomes greatly amplified by the time its effects reach the summit. For giant predators, the biological mathematics become exceptionally demanding. At its greatest estimated size, Megalodon reached approximately 17.9 meters, which is about 59 feet. Sustaining an animal of that scale required roughly 98,000 calories every day, an amount estimated to be about 20 times greater than the daily requirement of an adult great white shark. Such extraordinary energy demands could only be met within ecosystems producing immense quantities of prey without interruption. A slight reduction in available food might pass unnoticed by smaller predators. Yet for an animal requiring such enormous daily intake, even gradual decline carried profound consequences. Scarcity also transforms the relationships between predators themselves. When prey remains abundant, several large hunting species may occupy overlapping environments while avoiding direct competition because resources are sufficient for all. As prey populations slowly diminish, that balance begins to disappear. Each successful hunt becomes more valuable, while opportunities become less frequent. Competition intensifies not through dramatic confrontations, but through increasing overlap in diet, hunting grounds, and seasonal movement. Predators capable of surviving on a wider variety of prey or functioning under broader environmental conditions gradually gain an advantage over highly specialized hunters. The pace of reproduction further deepens this vulnerability. Massive predators mature slowly, investing years in growth before reaching reproductive age. They produce relatively few offspring during each breeding cycle, and those young require considerable time before joining the adult population. If prey abundance falls for only a comparatively brief geological interval, predator numbers may continue declining long after food begins returning. Their biological rhythm is simply too slow to rebuild populations rapidly. Recovery becomes delayed by generations, leaving even temporary shortages capable of producing lasting consequences. Ecologists describe another consequence through the concept of a trophic cascade, a chain of ecological effects that spreads through every level of a food web after a top predator is reduced or removed. Although the phrase emphasizes the disappearance of predators, the same interconnected structure also works in reverse. When prey populations collapse, every level above and below responds. Predators decline because food has become insufficient. Species previously controlled by those predators may later increase if conditions improve, altering competition among smaller animals. The entire ecosystem reorganizes as each biological layer adjusts to changes occurring elsewhere within the web of life. The fossil record shows that prey base collapse rarely develops without deeper environmental causes. Climate shifts alter migration routes and breeding habitats. Tectonic changes reshape coastlines, ocean currents, and productive feeding grounds. Sea level fluctuations remove shallow environments where countless prey species reproduce. These physical changes first influence the organisms nearest the base of the food web, yet their consequences travel steadily upward until they reach the largest hunters. By the time apex predators begin disappearing from ancient sediments, the ecological transformation responsible has often been unfolding for thousands of years. Their extinction, therefore, represents the final expression of a collapse that began much lower within the living architecture of the ocean, where countless smaller lives quietly determined the fate of its greatest predators. Among all the vanished rulers of the prehistoric ocean, none leaves a clearer trail toward its own disappearance than Megalodon. Its extinction, now estimated through optimal linear estimation to have occurred approximately 3.51 million years ago during the early Pliocene, provides perhaps the most detailed example of a giant predator undone not by a stronger rival, but by the gradual collapse of the living world beneath it. Fossil evidence from different regions suggests the disappearance may not have happened everywhere at exactly the same time, hinting that its decline unfolded unevenly as environmental conditions shifted from one ocean basin to another. For roughly 20 million years, beginning during the early Miocene, Megalodon occupied warm, shallow coastal seas where marine mammals flourished in extraordinary diversity. Smaller baleen whales were abundant, along with seals, dolphins, and many other large animals that formed a remarkably productive prey base. These coastlines supplied everything a predator of immense size required. Food was plentiful, nursery habitats were extensive, and favorable temperatures stretched across broad tropical and subtropical waters. For millions of years, those conditions appeared remarkably stable. The turning point arrived not through volcanic catastrophe or sudden climate upheaval, but through the slow movement of continents. Around 3 million years ago, the Central American Seaway, the ocean passage that had long connected the Atlantic and Pacific Oceans between North and South America, finally closed as the Isthmus of Panama rose above sea level. A corridor that had allowed seawater to circulate freely for millions of years gradually disappeared, redirecting currents that had previously carried warm tropical water toward higher latitudes. This geological change altered the circulation of the global ocean. Tropical and subtropical waters cooled over extended periods, while patterns of nutrient transport and heat distribution shifted across entire ocean basins. Productive ecosystems moved with these changing currents. The warm coastal habitats where Megalodon had prospered became less extensive, while many of the baleen whales upon which it depended either declined in number or migrated toward cooler polar waters that lay beyond the predator's preferred thermal environment. The consequences reached far beyond a single species. During the Pliocene marine megafauna extinction, approximately 36% of all large marine species disappeared. Around 55% of marine mammals vanished, together with approximately 35% of seabirds and roughly 43% of sea turtles. These losses reveal an ecological restructuring rather than an isolated extinction. Entire communities were adjusting to changing climates, altered coastlines, and reorganized food webs. Megalodon happened to occupy the highest position within one of the systems undergoing the greatest transformation. At the same time, new competitors expanded into the changing oceans. Early ancestors of the modern great white shark possessed smaller bodies, lower energy requirements, and greater tolerance for cooler waters. As whale populations shifted toward higher latitudes, these adaptable hunters could follow. Early orca lineages were also becoming increasingly successful, adding another efficient marine predator capable of exploiting many of the same prey resources. Competition did not depend upon direct conflict. It emerged because multiple predators were drawing energy from an increasingly limited supply of food. For an animal requiring immense daily nourishment, these changes reinforced one another with remarkable efficiency. Shrinking habitat reduced hunting opportunities. Declining prey populations increased the distance between successful hunts. Expanding competitors captured a greater share of the remaining food. Slow reproduction prevented populations from recovering once numbers began falling. None of these pressures alone necessarily guaranteed extinction, yet together they formed a convergence from which there was little possibility of recovery. The disappearance of Megalodon, therefore, reflects far more than the loss of a single giant shark. It demonstrates how slowly unfolding geological events can redirect ocean circulation, reshape ecosystems, redistribute prey, and ultimately determine the fate of even the most dominant marine predator. Long before the last Megalodon vanished from the sea, the conditions that had once made its existence possible had already begun slipping away, one current, one coastline, and one migrating whale at a time. The surface of the earth appears enduring when measured against a human lifetime, yet beneath that appearance, the continents are always moving. Their motion is almost impossibly slow, advancing only a few centimeters each year, a distance smaller than the width of a human hand. Across millions of years, however, these gradual movements redraw the outlines of entire oceans. Coastlines migrate, Seaways open and close, and habitats that once supported thriving marine ecosystems are transformed into something entirely different. For apex predators, these geological changes became another powerful path toward extinction. This process is known as plate tectonics, the continual movement of the enormous sections of Earth's crust that carry continents and ocean basins across the planet's surface. These shifting plates do not simply rearrange land, they reshape the ocean itself. As continents drift together, marine corridors connecting distant regions can disappear, isolating populations that once exchanged genes across vast distances. When plates separate, entirely new ocean basins emerge, creating fresh circulation pathways that redirect heat, nutrients, and marine life into unfamiliar patterns. Every alteration to the shape of an ocean influences the currents flowing through it. A newly opened passage may strengthen circulation between distant basins, while a narrowing channel can slow or redirect currents that have existed for millions of years. These changes determine where warm water travels, where cold, nutrient-rich water reaches the surface, and where productive ecosystems develop. Large marine predators rarely respond directly to the movement of continents. Instead, they respond to the changing distribution of prey, breeding habitats, and favorable environmental conditions that plate tectonics gradually creates. Among the most vulnerable environments are the shallow continental shelves bordering the continents. These broad underwater plains receive abundant sunlight, support rich plankton production, and sustain enormous populations of fish, marine reptiles, and marine mammals. Because they lie along continental margins, they are especially sensitive to tectonic movement. Even modest uplift or subsidence unfolding across geological time can greatly alter the extent of these productive habitats. A coastline that once extended across broad, shallow waters may retreat into deeper seas, while another region may become newly flooded, temporarily creating favorable conditions before changing once again. Sea level adds another layer to this continual transformation. During intervals of extensive glaciation, enormous volumes of water become locked within continental ice sheets, lowering global sea level. Vast portions of continental shelves may then emerge above the ocean, eliminating habitats that had supported marine communities for millions of years. During warmer intervals, melting ice and thermal expansion raise sea level, flooding continental interiors with broad, shallow seas that can flourish for long periods before eventually retreating as conditions change. These repeated advances and withdrawals continually reshape the geography upon which marine ecosystems depend. For apex predators, the consequences extend beyond hunting grounds alone. Many species rely upon protected coastal environments where their young can mature with reduced exposure to larger predators and abundant access to food. These nursery grounds occupy the shallowest parts of continental shelves, making them especially vulnerable to changing sea levels and tectonic movement. If uplift raises these regions above the water or falling sea levels expose them to the atmosphere, suitable breeding habitat may disappear even while adult predators continue surviving offshore. Reproduction slows, young animals become fewer, and populations begin declining despite the continued presence of mature individuals. Unlike volcanic eruptions or abrupt climatic disturbances, plate tectonics rarely produces immediate biological crises. Its influence accumulates gradually, altering the geography of oceans with remarkable patience. Over immense spans of time, migration routes become fragmented, productive coastlines shift, circulation patterns evolve, and nursery habitats appear and vanish. Each individual change may seem modest, yet together they steadily redefine the conditions supporting marine life. Apex predators inherit these altered worlds generation after generation, adapting whenever possible, but remaining dependent upon coastlines and shallow seas whose locations are never permanent. In this way, the slow movement of continents becomes one of the most persistent architects of extinction, reshaping the map of the oceans long before the disappearance of their greatest hunters becomes visible in the fossil record. There are moments in Earth's history when the disappearance of a single ocean altered the course of life across the entire planet. The change unfolded so gradually that no living creature could have recognized it within a lifetime. Generation followed generation, while coastlines shifted almost imperceptibly. Yet over immense stretches of geological time, an ocean that had once stretched across the equator slowly unraveled into scattered fragments. Its passing reshaped the pathways of currents, climates, and the destinies of the predators that had flourished within its waters. The Tethys Sea was among the defining oceans of the Mesozoic world. Extending across the tropical belt between the ancient continents, it formed a broad expanse of warm, shallow water-linking regions that would one day become the Mediterranean, the Middle East, and the Indo-Pacific. Along the margins of the southern supercontinent known as Gondwana, sunlight reached the seafloor across immense continental shelves, nourishing abundant plankton, reefs, fish, marine reptiles, and countless other forms of life. For hundreds of millions of years, this uninterrupted marine corridor supported layered food webs capable of sustaining successive dynasties of apex predators. The strength of the Tethys did not lie only in its size. Its greatest gift was continuity. Animals could disperse across vast tropical habitats without encountering major barriers. Populations remained connected through constant movement, allowing genes, prey species, and ecological relationships to flow across an enormous living network. Predators occupying distant coastlines were still part of the same expansive ecosystem, linked by waters that carried nutrients and life from one region to another. That continuity slowly began to dissolve as Africa drifted northward toward Eurasia. Beginning about 100 million years ago, that is nearly 62 million miles in geological time, is not applicable because this span measures time rather than distance. The advancing continents steadily narrowed the Tethys. What had once been a broad equatorial seaway gradually fragmented into smaller basins separated by rising land and constricted passages. This transformation unfolded across tens of millions of years, each stage subtly altering the geography upon which marine ecosystems depended. As the seaway narrowed, ocean circulation also changed. Warm equatorial currents that had once crossed the globe through the Tethys encountered growing obstacles, forcing the oceans to reorganize their pathways. Heat was redistributed differently between the tropics and higher latitudes. Regions that had long experienced stable conditions developed new temperature gradients, while nutrient delivery shifted as currents found unfamiliar routes around emerging continents. Productive ecosystems did not disappear everywhere at once, yet their distribution became increasingly uneven as the geography guiding the oceans evolved. The consequences reached far beyond changing currents. Populations that had once occupied a continuous tropical habitat became divided into isolated refuges. Groups separated by newly formed land barriers could no longer exchange individuals freely. Genetic diversity declined within many isolated populations, while local ecological disturbances became increasingly difficult to overcome through migration from healthier regions. A predator confined to one shrinking basin depended entirely upon the stability of that basin, with fewer opportunities for recovery if prey declined or environmental conditions deteriorated. Isolation also narrowed the intricate food networks that had once stretched across the length of the Tethys. Large predators depended upon abundant prey moving through connected ecosystems, but fragmentation reduced both movement and resilience. Local disruptions no longer remained local. A decline within one enclosed basin could no longer be balanced by immigration from distant populations. Gradually, the expansive ecological fabric supporting generations of marine hunters unraveled into separate pieces, each more vulnerable than the uninterrupted whole that had existed before. Today, the Mediterranean Sea, the Black Sea, the Caspian Sea, and the Aral Sea remain as scattered descendants of that vanished ocean. They preserve only fragments of a marine world that once encircled the equator and nourished some of the richest predator communities in Earth's history. Their existence offers a reminder that oceans themselves possess life histories. They are born through the movement of continents. They evolve as currents reshape their waters, and they may ultimately fade into isolated remnants, carrying with them entire ecosystems that had once seemed as enduring as the horizon itself. Long before the fossil record reveals the disappearance of a familiar giant, another story has already begun beneath the surface. It is a story with few dramatic encounters and almost no decisive battles. Instead, it unfolds through countless generations as one lineage slowly becomes better suited to an ocean that is no longer the one its rivals evolved to dominate. By the time the change becomes unmistakable in ancient rock, the outcome has already been written across thousands of years of gradual replacement. Competitive displacement is the emergence of new predator lineages whose biological characteristics allow them to thrive under conditions that increasingly challenge established apex hunters. This process becomes most powerful when the ecosystem is already weakened. A healthy ocean rich with prey can support several large predators occupying similar ecological roles. Abundance softens competition because food is available across broad regions, allowing different hunters to exploit overlapping resources without exhausting them. That balance changes once the foundation of the ecosystem begins to narrow. Cooling climates alter migration routes, warming seas reshape habitats, tectonic movements transform coastlines, and declining prey populations reduce the energy flowing upward through the food web. The same environment that once sustained several dominant predators can no longer meet the demands of all of them. Every successful hunt becomes more significant, every breeding season more uncertain, and every generation more dependent upon traits that fit the changing world rather than the old one. The competition itself rarely resembles direct conflict. Fossil evidence does not suggest endless battles between rival giants struggling for dominance. Instead, competitive displacement is a prolonged contest for shared resources. One lineage gradually expands into habitats where another once flourished. Feeding grounds overlap more frequently. Juveniles compete for the same prey. Reproductive success differs by only small amounts from one generation to the next, yet those differences accumulate across immense spans of time. The fossil record eventually preserves the result as one geographic range steadily contracts while another spreads across newly favorable waters. The characteristics that determine success are never fixed. They change alongside the ocean itself. During periods of environmental stability, enormous size and specialized hunting strategies may provide remarkable advantages. Large bodies permit greater strength, powerful swimming, and the ability to pursue substantial prey that smaller predators cannot subdue. Yet those same characteristics become costly when prey becomes less dependable. A predator requiring immense daily energy cannot easily reduce its needs, while a smaller hunter survives upon fewer successful captures and can endure longer intervals between meals. Dietary flexibility also becomes increasingly valuable. A specialized predator adapted to a narrow range of prey may struggle when those animals decline or migrate beyond suitable habitat. Another lineage, capable of feeding upon fish, marine mammals, squid, or carrion, gains opportunities unavailable to its more selective competitor. Reproductive strategy contributes another advantage. Species reaching maturity more rapidly and producing offspring more frequently recover from population losses with greater efficiency than slowly reproducing giants whose generations span many years. Cold tolerance may become equally important as ocean circulation changes. Predators capable of following prey into cooler waters gain access to resources unavailable to species physiologically restricted to warmer environments. As productive ecosystems shift toward different latitudes, adaptable hunters accompany them, while specialists remain confined to shrinking habitats whose biological richness steadily diminishes. No single adaptation guarantees success, yet together these traits shape survival under changing environmental conditions. Competitive displacement, therefore, acts less like a sudden conquest than an adjustment of ecological balance. It follows disturbances already set in motion by changing climate, shifting continents, declining oxygen, or collapsing food webs. The new predators do not create the instability. They inherit an altered ocean and happen to possess characteristics better matched to its emerging conditions. The older rulers gradually fade, not because they became weaker than they had once been, but because the world that had favored their remarkable strengths no longer existed in the same enduring form. The final chapters of a great predator rarely begin with the predator itself. They begin with the gradual narrowing of possibilities. Feeding grounds become fewer, familiar migration routes no longer lead to the same abundance, and each generation inherits a world slightly less favorable than the one before it. By the early Pliocene, these converging changes were shaping one of the clearest examples of competitive displacement preserved in the fossil record: the overlapping rise of the great white shark and the decline of Megalodon. The species known today as the great white shark, Carcharodon carcharias, emerged during the same broad interval that Megalodon was approaching extinction. This overlap was not simply a coincidence of chronology. It placed two highly capable marine predators within an ocean already transformed by cooling climates, shifting currents, and shrinking distributions of the marine mammals upon which both depended. Yet these predators entered that changing environment with profoundly different biological advantages. The great white shark never approached the immense proportions of Megalodon. Its smaller body required far less energy each day, allowing it to survive on a prey supply that could no longer sustain a giant. Its physiology also permitted successful hunting across cooler waters, extending its range well beyond the warm coastal habitats favored by its larger relative. In an ocean whose productive ecosystems were gradually shifting toward higher latitudes, that flexibility became an increasingly valuable advantage. As global cooling continued after the closure of the Central American Seaway, many populations of baleen whales altered their migrations, spending more time in colder regions where nutrient-rich waters supported abundant feeding. The great white shark could accompany those movements, remaining connected to the expanding centers of marine productivity. Megalodon, whose evolutionary history had been closely tied to warm, shallow seas, found those colder environments increasingly inaccessible. Suitable habitat compressed toward lower latitudes, even as its principal prey became less predictable within that narrowing range. The result was not merely a reduction in available food, It was an intensification of competition for every remaining opportunity. Both predators relied heavily upon large marine mammals, yet only one could exploit the growing abundance, developing beyond the limits imposed by warm water specialization. The advantage accumulated gradually across countless generations. A predator capable of following prey wherever environmental conditions carried it possessed opportunities that a more specialized rival could no longer reach. Another competitor was also becoming increasingly important during this same interval. Early lineages leading toward the modern orca expanded within many marine ecosystems. Unlike solitary hunters dependent primarily upon physical size, these highly social marine mammals employed coordinated hunting strategies supported by advanced communication and learned behavior. Their flexibility allowed them to pursue a remarkable diversity of prey, including animals occupying ecological spaces already under increasing pressure. Rather than replacing either shark directly, they further compressed the remaining resources available to every large predator sharing those waters. None of these forces alone fully explains the disappearance of Megalodon. Habitat contraction, declining prey, expanding competitors, and immense metabolic demands acted together, reinforcing one another until escape became biologically improbable. Scientists describe such circumstances as an ecological trap, a convergence in which every available path becomes progressively less favorable. Adaptations that had supported extraordinary success for millions of years became increasingly mismatched to an ocean whose physical and biological character had fundamentally changed. The fossil record preserves this transition with remarkable subtlety. Evidence suggests that Megalodon did not vanish everywhere at precisely the same moment. Some regions appear to have lost their populations earlier than others, reflecting the uneven pace at which habitats contracted and prey distributions shifted across the world's oceans. This geographically asynchronous pattern matches the expectation of gradual ecological compression rather than a single sudden catastrophe. By the time the last populations disappeared, the transformation had already unfolded across ages, leaving behind an ocean where different predators now occupied the places once ruled by the greatest shark that had ever lived. Chemistry can reshape an ocean as profoundly as shifting continents or changing climate. The transformation is almost impossible to witness from one lifetime to the next, yet it unfolds through countless invisible reactions taking place within every drop of seawater. Long before the largest predators begin to disappear, the foundations supporting their world may already be dissolving beneath them, molecule by molecule, until an ecosystem that once appeared enduring begins to lose the structures upon which its abundance depended. Ocean acidification is a chemical process distinct from ocean anoxia, even though both ultimately erode the same living networks. It begins when increasing amounts of carbon dioxide dissolve into seawater. The dissolved gas combines with water to form carbonic acid, a weak acid that lowers the ocean's potential of hydrogen, a measure describing how acidic or alkaline a liquid is. This gradual shift in seawater chemistry changes the balance of dissolved minerals required by countless marine organisms, altering conditions that had remained favorable across vast spans of geological time. Many of the animals most affected are not large or powerful. Reef-building corals, shell-forming mollusks, echinoderms such as sea urchins and sea stars, and tiny plankton that construct delicate calcium carbonate shells all rely upon stable carbonate chemistry to build and maintain their protective structures. Their skeletons and shells are not merely protective coverings. They are the architecture supporting entire marine communities. Reefs provide shelter for young fish, feeding grounds for countless invertebrates, and intricate habitats where thousands of species complete different stages of their lives. As acidification intensifies, constructing these calcium carbonate structures becomes increasingly difficult. Existing skeletons may weaken while new growth slows or ceases altogether. Reef frameworks that accumulated across thousands of years gradually lose their resilience. Open spaces once crowded with marine life become less capable of supporting the extraordinary diversity that had depended upon them. The change rarely begins with the disappearance of predators. Instead, it starts among the smallest builders whose work creates the physical landscape upon which richer ecosystems depend. The consequences then move upward through the food web with remarkable consistency. Smaller fishes lose breeding grounds and shelter from larger hunters. Invertebrate populations decline as their habitats deteriorate. Species occupying the middle levels of the ecosystem encounter fewer feeding opportunities and reduced reproductive success. By the time these changes reach apex predators, the damage has already traveled through every level below them. Large hunters discover fewer prey animals, not because they themselves have changed, but because the biological infrastructure supporting abundance has steadily unraveled beneath them. Evidence preserved within rocks from the Permian-Triassic boundary indicates that this process did not occur in isolation. Geochemical signatures reveal that ocean acidification and ocean anoxia operated together during that extraordinary crisis. While deep waters were losing oxygen, the chemistry governing carbonate formation was also shifting against reef builders and shell-producing organisms. The ocean was therefore experiencing two distinct chemical disruptions at the same time. One reduced the availability of oxygen required for complex life, while the other undermined the very structures supporting productive shallow ecosystems. Their combined effects explain why recovery required such immense spans of geological time rather than a brief return to earlier conditions. Ocean acidification is therefore not a background influence acting with gentle persistence alone. During intervals when atmospheric carbon dioxide rises rapidly, seawater chemistry can approach critical thresholds beyond which carbonate-dependent organisms experience abrupt and severe decline. Once those thresholds are crossed, reefs may deteriorate far more quickly than they formed, carrying entire communities with them. The disappearance of great marine predators is often remembered in the fossil record, yet the earliest losses belong to the unseen builders whose fragile skeletons once held together the living foundation of the ancient sea. The outline of an ancient shoreline was never fixed. Across the deepest reaches of geological time, the boundary between land and sea advanced and retreated with remarkable persistence, redrawing coastlines that no map could preserve for long. Every shift altered more than the appearance of the planet. It transformed the narrow margins where sunlight, nutrients, and shelter combined to produce the richest marine environments, places that nurtured not only abundant prey, but also the earliest lives of the ocean's greatest hunters. Sea level change is driven by several powerful forces acting across different spans of time. During intervals of widespread glaciation, immense quantities of water became locked within continental ice sheets. As a result, global sea levels fell dramatically. At the greatest extent of these glacial periods, the ocean surface dropped by approximately 120 meters, which is about 394 feet. Broad continental shelves that had once rested beneath shallow water emerged into the open air, removing some of the most productive marine habitats on Earth. These continental shelves were never empty expanses. Their relatively shallow depth allowed sunlight to penetrate the water, encouraging dense growth of microscopic life that supported intricate food webs. Nutrients circulated efficiently through these coastal environments, sustaining fishes, marine reptiles, sharks, shell-building organisms, and countless invertebrates. Large predators repeatedly concentrated their hunting within these regions because the abundance of prey justified the tremendous energy required to sustain massive bodies. When falling sea levels exposed these shelves, the biological foundation supporting that abundance disappeared with them. The pattern reversed during warmer intervals. Expanding oceans spread across continental margins, flooding low-lying landscapes and creating extensive inland seas that endured for millions of years. These temporary expansions opened fresh habitats where marine communities flourished. New coastlines formed, nursery grounds multiplied, and productive feeding areas extended across regions that had previously remained dry. Yet these gains were never permanent. As tectonic activity continued and climate gradually shifted once more, many of these shallow seas slowly withdrew, leaving behind sediments filled with fossils that recorded ecosystems existing only for a limited chapter of Earth's history. One remarkable example was the Western Interior Seaway, which stretched across the heart of what is now North America during the Cretaceous period. This broad inland sea separated the continent into eastern and western land masses, while supporting a thriving marine ecosystem unlike any surrounding ocean. Large reptiles, fishes, ammonites, and formidable predators occupied its waters for millions of years. Eventually, regional uplift and mountain building altered the landscape, and the seaway gradually vanished. The disappearance was not merely the loss of water, it marked the disappearance of an entire ecological setting that countless species had evolved to inhabit. Among the environments most vulnerable to every rise and fall of the sea were nursery grounds. These sheltered coastal waters provided conditions uniquely suited to young apex predators. Smaller bodies could develop where food was plentiful and larger competitors were less common. Survival during these earliest stages determined whether future generations would ever reach maturity. Because nursery grounds occupied the shallowest margins of the ocean, they were also the first places eliminated when sea levels declined. A coastline retreating only modestly across geological time could erase habitats that had supported reproduction for countless generations. The consequences unfolded gradually rather than all at once. Adult predators, already established within the open ocean, often continued hunting successfully for many years. Their presence could create the appearance of stability even as fewer young animals entered the population. Each passing generation became smaller than the last, not because adults vanished suddenly, but because successful recruitment steadily diminished. The population slowly aged, and natural mortality eventually exceeded replacement. In the fossil record, this appears as a prolonged fading rather than an abrupt disappearance, revealing that the loss of nursery grounds could reshape the destiny of even the mightiest marine predators without a single dramatic moment announcing the change. There is a hidden contradiction carried by every ruler of the sea. Across hundreds of millions of years, the greatest marine predators repeatedly reached extraordinary heights of success, only to discover that the very adaptations which elevated them above every rival also narrowed the paths by which they could survive. Evolution rewarded dominance generously, yet it attached conditions that became visible only when the surrounding world began to change. Large body size offered remarkable advantages, while the ocean remained rich and productive. An immense predator could overpower prey beyond the reach of smaller hunters, defend valuable feeding grounds, and travel immense distances with confidence born from strength. Such size often discouraged direct competition, allowing a mature hunter to occupy the highest place within its ecosystem. Beneath these obvious advantages, however, rested an equally immense demand. Every movement required substantial energy. Every hunt had to repay an enormous biological investment, and every successful day depended upon the continued abundance of large prey. Great size was not merely an achievement, it became a permanent obligation. That obligation shaped every aspect of an apex predator's existence. A body built to pursue powerful prey required an equally powerful flow of nourishment. If prey populations declined only modestly, the consequences were amplified at the highest level of the food web. Smaller predators could often persist by pursuing different prey or reducing their energy expenditure. The largest hunters possessed far less flexibility. Their bodies had evolved around abundance, not scarcity, and every decline beneath them echoed upward with increasing force. The rhythm of reproduction deepened this vulnerability. Large marine predators matured slowly, sometimes requiring many years before producing offspring. Each generation represented an enormous investment of energy, and relatively few young entered the population during each reproductive cycle. This strategy worked efficiently when adults survived for long periods within stable environments, because each individual contributed to the population across many seasons. When disruption arrived, however, recovery became remarkably difficult. Even if environmental conditions briefly improved, too few young animals were available to replace losses before another challenge emerged. Specialization added another layer to the paradox. Over immense spans of evolutionary time, natural selection, refined hunting techniques, body proportions, sensory abilities, and behavior toward particular kinds of prey. Such refinement produced extraordinary efficiency under familiar conditions. A predator adapted to pursue large marine mammals, swift fishes, or armored reptiles became exceptionally skilled within that ecological role. Yet specialization also reduced flexibility. When preferred prey declined, migrated, or disappeared, changing to entirely different food sources was rarely a simple adjustment. Millions of years of evolutionary refinement could not be rewritten within a handful of generations. The geography required by these animals expanded the challenge still further. Apex predators depended upon productive environments extending across enormous stretches of ocean. Their hunting grounds often covered thousands of kilometers, that is nearly 621 miles, for every 1,000 kilometers considered across such migrations, linking coastlines, continental shelves, and open waters into a single living network. A disruption in circulation, temperature, chemistry, or prey abundance affecting only part of that network could influence populations separated by vast distances. Because the ecological system functioned as an interconnected whole rather than a collection of isolated habitats. Viewed together, these characteristics reveal an enduring pattern repeated throughout Earth's history. Strength encouraged greater size. Greater size encouraged slower reproduction. Specialized hunting increased efficiency while reducing adaptability. Expansive territories maximized opportunity while increasing exposure to planetary change. Each successful adaptation strengthened the predator during long intervals of environmental stability, yet each simultaneously increased dependence upon conditions remaining much the same. The ocean never promised such permanence. Continents drifted, currents shifted, climates warmed and cooled, coastlines advanced and retreated, and food webs continually reorganized themselves across geological time. Against that moving backdrop, Apex predation emerged as one of evolution's most impressive achievements, but also one of its most delicate bargains. The strategy flourished magnificently while the sea continued to support it, then gradually unraveled whenever the living foundations beneath it began to change. An apex predator leaves behind more than an empty place when it disappears. Its absence begins a gradual rearrangement that spreads through every connected layer of the living ocean, altering relationships that had developed across immense spans of time. Biologists describe this process as a trophic cascade, a chain of ecological consequences that travels downward through the food web after the highest level has been removed. What vanishes is not simply a hunter. What changes is the balance that had quietly shaped countless lives beneath it. While an apex predator remains present, it influences far more than the animals it captures. The possibility of predation affects where prey gather, how long they feed, the routes they travel, and the habitats they avoid. Population size is only part of the story. Behavior itself becomes an ecological force. The highest predator establishes boundaries that prevent any single prey species from dominating the community. Those boundaries allow many different organisms to share the same environment without one overwhelming the others. When that influence disappears, the first changes often appear among the former prey. Freed from continual predation, their populations can expand beyond previous limits. Larger numbers consume greater quantities of food, placing increasing pressure upon the organisms occupying the next level beneath them. Herbivores graze more intensely. Mid-level predators capture more fishes and invertebrates. Species that once existed within balanced proportions begin growing at different rates, and the effects spread steadily through habitats that may appear unchanged from the surface. Modern marine ecosystems provide remarkable illustrations of this process. Along the Northwest Atlantic, the severe decline of cod populations reshaped entire coastal food webs. Species that had previously been restrained expanded rapidly, altering predator and prey relationships across broad regions of the seafloor. Communities living upon the bottom changed in composition, while the abundance of many smaller organisms shifted in response. The disappearance of one dominant predator gradually transformed an ecological network that had developed over countless generations. Another well-documented example emerged along the Pacific coast following declines in sea otter populations. Sea otters normally limit the abundance of sea urchins, preventing them from consuming underwater forests of kelp faster than those habitats can recover. Where sea otters became scarce, sea urchin populations expanded dramatically. Extensive kelp forests declined, removing shelter and feeding grounds for numerous fishes and invertebrates. A change, beginning with one predator, ultimately altered the physical appearance and biological productivity of entire coastal ecosystems. These examples reveal that the ocean existing after an apex predator disappears is not merely the previous ecosystem with one species missing. The relationships connecting every level of the food web are reorganized. Population sizes adjust to new conditions, feeding strategies evolve along different paths, and habitats begin supporting different combinations of life. Eventually, the altered ecosystem may settle into another stable condition, yet that stability reflects a fundamentally different biological arrangement from the one that came before. The fossil record preserves traces of similar transformations, extending far beyond human observation. After prehistoric apex predators vanished, paleontologists often discover abrupt changes in the relative abundance of mid-level predators, grazing animals, shell-building organisms, and other members of ancient marine communities. Entire assemblages appear to reorganize within comparatively brief geological intervals. Rather than recording the disappearance of a single lineage in isolation, the rocks preserve evidence that the surrounding ecosystem changed with it. These cascading effects can also strengthen themselves over time. As ecological relationships shift farther from their previous balance, the altered environment may become less capable of supporting another predator occupying the same role. Prey communities evolve under different pressures, habitats continue changing, and energy flows through the food web along new pathways. Recovery therefore depends upon more than the arrival of another powerful hunter. The living architecture supporting apex predation must gradually rebuild from its foundations, a process that often unfolds across spans of time so immense that entire chapters of Earth's history pass before the highest place in the ocean is fully occupied once again. A single thread rarely unravels an ancient dynasty. The history preserved within layers of stone reveals a more intricate design, one in which several changes gather gradually before reaching a shared point of consequence. Across the long succession of marine apex predators, the same structure appears again and again. The disappearance of a dominant lineage almost never follows one overwhelming disaster alone. Instead, it emerges from the convergence of several pressures that reinforce one another until resilience itself is exhausted. Each individual pressure possesses its own rhythm. Volcanic eruptions reshape the atmosphere over immense spans of time. Ocean circulation shifts as continents continue their patient movement. Temperatures rise or fall, altering habitats and redistributing prey. Chemical conditions within seawater change as increasing amounts of carbon dioxide dissolve into the ocean. Any one of these developments may challenge an ecosystem, yet life often demonstrates a remarkable capacity for adjustment when disruption arrives by only one pathway. The greatest biological crises unfold when these pathways intersect. During the Permian extinction, prolonged volcanic activity released extraordinary quantities of carbon dioxide into the atmosphere. Global warming intensified, ocean circulation weakened, dissolved oxygen declined, and increasing acidity placed additional pressure upon reef-building organisms and shell-forming life. None of these forces acted in complete isolation. Each amplified the effects of the others until the combined burden exceeded the capacity of marine ecosystems to maintain their previous structure. The result was not simply an extinction pulse, but the greatest collapse of complex marine life known from the geological record. A remarkably similar pattern appears much later in the story of Megalodon. The closing of an ancient seaway altered global circulation and encouraged prolonged climatic cooling. Productive warm water habitats contracted. Important prey populations declined or shifted toward colder regions. Changes in sea level reduced valuable nursery grounds, while increasingly successful competitors expanded into ecological space that had once belonged almost entirely to the giant shark. None of these developments alone necessarily guaranteed extinction. Together, they created a web of pressures from which recovery became progressively less likely. The marine predator losses during the middle of the Cretaceous period followed the same underlying architecture despite involving different species and different environmental conditions. Exceptional warmth spread across the oceans, while extensive oxygen depletion developed within deeper waters. Changes in nutrient cycling altered the biological productivity supporting prey populations. Predator lineages that had endured for more than 100 million years gradually disappeared as several environmental disturbances overlapped within a comparatively brief geological interval. Their remarkable longevity offered little protection once multiple systems of the ocean began changing together. This recurring pattern reflects the biology of apex predators themselves. Large hunters possess enough resilience to withstand an isolated challenge if favorable conditions return before populations decline too severely. Their long lives allow experienced adults to remain within the ecosystem, and surviving individuals can eventually produce new generations. Recovery, however, requires time. Slow maturation and limited reproduction mean that rebuilding populations cannot happen rapidly. When a second or third stress arrives before recovery has begun, the opportunity for stabilization steadily narrows. Each additional pressure also strengthens the influence of those already present. Reduced prey abundance magnifies the effects of habitat loss. Habitat loss intensifies competition. Competition becomes more severe as environmental conditions continue deteriorating. Rather than adding together in simple fashion, these forces interact continuously, creating consequences greater than any single cause could produce alone. The ecological balance supporting apex predators gradually shifts until the accumulated burden reaches a biological threshold beyond which decline accelerates. This explains why many extinctions appear sudden within the fossil record, even though their causes developed over immense spans of time. The environmental changes themselves often advanced gradually across hundreds of thousands or millions of years. What seems abrupt is the moment when several long, unfolding processes finally converged. At that point, the remaining margin for recovery disappeared, and the dominant predators that had endured countless earlier challenges quietly passed into the deeper history of the sea. Recovery, in the language of deep time, bears little resemblance to restoration. When an extinction event reaches the highest levels of the marine food web, the disappearance of dominant predators is only the beginning of a far longer transformation. The oceans do not simply refill with familiar life, nor do ancient ecosystems return once the immediate crisis has passed. Instead, the living world begins again from whatever fragments have managed to endure, assembling an entirely different future from the remains of the old. After the Permian extinction, the seas entered an interval that paleontologists often describe as an age of disaster fauna. The organisms that persisted were rarely those that had defined the preceding world. Many were ecological generalists, species able to tolerate unstable environments, reduced oxygen, disrupted chemistry, and food webs stripped of much of their former complexity. Survival no longer favored dominance within an abundant ecosystem. It favored flexibility, modest biological demands, and the capacity to endure conditions that had become hostile to many specialized forms of life. The disappearance of established predators left ecological space unoccupied, yet that space remained difficult to reclaim. An apex predator cannot exist without abundant prey, and abundant prey cannot exist without healthy populations beneath them. Every layer depends upon another. Before large hunters could return, countless smaller relationships had to be rebuilt, beginning with organisms that stabilized sediments, recycled nutrients, filtered seawater, and supported the intricate foundation upon which larger communities ultimately depended. Among the earliest groups to begin expanding, once conditions gradually improved, were free-swimming predators inhabiting the open water. Their appearance signaled that parts of the food web had begun functioning once more. Even so, the benthic communities living across the seafloor recovered at a much slower pace. These organisms formed the enduring biological foundation supporting broader marine productivity, and their diversity remained greatly diminished throughout much of the Triassic period. The rebuilding of this hidden layer unfolded gradually across millions of years, limiting how rapidly the upper levels of the ecosystem could recover. Only after approximately 10 million years had passed did newly evolving marine reptile lineages diversify enough to establish themselves as dominant predators within the recovering seas. Their emergence did not represent the return of the vanished Permian rulers. They belonged to different evolutionary branches, possessed different anatomical designs, and interacted with prey that had also changed profoundly during the long interval of recovery. Dominance had returned, but it belonged to entirely new participants within an unfamiliar ecological stage. The ocean surrounding these new predators was fundamentally different from the one that had existed before the extinction. Food webs followed altered pathways. Communities were assembled from surviving lineages and recent evolutionary innovations rather than restored ancient partnerships. Even the balance between habitats shifted as ecosystems continued adapting to environmental conditions that had been permanently reshaped. Geological catastrophe had not merely interrupted the previous world. It had redirected the course of marine evolution onto another path altogether. This extended interval reveals how biological complexity cannot be reconstructed quickly once it has been dismantled. Individual species may evolve or spread across available habitats within comparatively shorter spans of geological time, yet a functioning ecosystem depends upon thousands of interactions developing together. Predators, prey, scavengers, filter feeders, decomposers, reef builders, and microscopic plankton all contribute to the stability that allows large hunters to persist. Every missing layer delays the return of those above it. The same broad pattern appears repeatedly throughout the fossil record. Recovery after major extinction events commonly extends across roughly 5 million to 10 million years before marine ecosystems regain comparable ecological complexity. These immense spans reflect not hesitation within evolution, but the extraordinary challenge of rebuilding interconnected food chains from damaged foundations. The sea remembers its former inhabitants only through stone, while each new age slowly composes a different living ocean, shaped not by what was lost, but by what remained capable of beginning again. The ocean carries within it a remarkable consistency. Across spans of time so immense that continents have wandered across the globe and mountain ranges have risen from ancient seabeds, the same broad patterns emerge again and again. The repetition is not the result of chance. It reflects a deeper architecture, a set of structural vulnerabilities woven into the way marine ecosystems are assembled. Whenever those underlying supports are disturbed in similar ways, life responds with strikingly familiar consequences. Every thriving ocean depends upon a surprisingly limited collection of physical and chemical conditions. Stable circulation distributes heat and nutrients across vast distances. Adequate oxygen supports animals from the smallest drifting organisms to the largest hunters. Balanced chemistry allows shells, reefs, and microscopic skeletons to form. Productive coastal habitats nurture young animals before they enter the wider sea. Together, these foundations sustain the elaborate food webs that eventually support apex predators. Remove enough of these supports at the same time, and even the most successful ecosystems begin to lose their balance. The forces capable of disturbing these foundations have existed throughout Earth's history. Massive volcanic outpourings can alter atmospheric chemistry and release enormous quantities of carbon dioxide. Shifting continents reshape ocean gateways, redirecting currents that have circulated for millions of years. Changes in global temperature influence oxygen distribution, sea level, and the productivity of marine habitats. None of these processes belong to a single chapter of Earth's past. They are recurring expressions of a dynamic planet whose surface and interior continue evolving across geological time. Most of the time, however, extinction unfolds at a far gentler pace. Species appear, adapt, and eventually disappear through the ordinary process known as background extinction. This continual replacement is the normal rhythm of evolution. New lineages emerge, while others gradually fade, often without disrupting the wider structure of the ecosystem. Marine communities absorb these modest changes because the supporting framework beneath them remains largely intact, allowing ecological relationships to adjust without widespread collapse. Mass extinctions represent something profoundly different. Rather than a gradual turnover of individual species, they occur when several vulnerability mechanisms become active together. Volcanic activity may coincide with warming oceans. Reduced oxygen may develop alongside changing chemistry. Tectonic rearrangement may compress habitats while food webs are already under strain. Each pressure weakens the resilience of the system until multiple thresholds are crossed within a comparatively brief geological interval. The result appears abrupt in the fossil record, even though the contributing forces often accumulated across many thousands or millions of years. This distinction has become one of the central principles of paleontology because it reveals that resilience is constantly being tested. During ordinary intervals, ecosystems experience small disturbances that many organisms successfully withstand. During rare intervals of convergence, those same ecosystems encounter several interconnected disruptions that overwhelm the capacity for recovery. The difference lies less in the existence of stress than in the number of stresses arriving together and reinforcing one another. These biological transitions are recorded with remarkable clarity in the rocks themselves. Around the world, geologists identify major extinction boundaries because the fossils above and below them differ so dramatically. Entire communities disappear, while unfamiliar assemblages emerge in succeeding layers. These changes are sufficiently consistent across continents that they provide reliable reference horizons for correlating sedimentary sequences separated by vast oceans. The living world has become one of the most dependable clocks preserved within Earth's crust. The same record also reveals another enduring pattern. Episodes involving enormous volcanic provinces repeatedly coincide with some of the greatest marine extinction events known to science. Their recurrence suggests that the geological engine capable of transforming the oceans has never ceased operating. It has simply continued its patient rhythm beneath the surface, while marine life has repeatedly adapted, diversified, and, at rare moments when several ancient forces converged once more, entered another chapter of profound biological change, far beneath the familiar surface of the oceans. Beyond the reach of tides and currents, another process has continued, almost without interruption, since the earliest chapters of Earth's history. It unfolds within the mantle, where immense reservoirs of heat slowly rise toward the crust. From these deep origins emerge the vast volcanic episodes known as large igneous provinces, among the most powerful geological forces ever to reshape the marine world. Their appearance across the fossil record is not exceptional. It is a recurring expression of the planet's internal engine, one whose influence reaches from the deepest rocks to the highest levels of the food chain. A large igneous province forms when an ascending mantle plume, a column of intensely heated material from deep within Earth, approaches the crust and releases extraordinary volumes of basaltic lava across continents or the ocean floor. Unlike familiar volcanic mountains that erupt from relatively confined vents, these events spread molten rock across immense regions over intervals lasting from tens of thousands to millions of years. Individual eruptions may pause and resume repeatedly, gradually constructing volcanic landscapes whose scale defies ordinary imagination, while steadily altering the chemistry of the atmosphere and oceans. Among the best-known examples are the Siberian traps, the Deccan traps, the Central Atlantic Magmatic Province, and the Vili traps. Although separated by vast spans of geological time, they reveal a striking pattern. Each corresponds closely with intervals during which marine ecosystems experienced profound biological disruption. The repetition of this association has transformed scientific understanding, shifting these volcanic provinces from geological curiosities into central explanations for some of the greatest extinction events preserved within Earth's history. The Central Atlantic Magmatic Province offers one of the clearest examples. Approximately 201 million years ago, enormous volcanic activity accompanied the closing chapter of the Triassic period. As basalt spread across an emerging landscape, volcanic gases entered the atmosphere, influencing climate and ocean chemistry across the globe. Marine communities experienced substantial losses, including many apex predator lineages that had flourished for millions of years. Their disappearance created ecological opportunities that would later be occupied by entirely new predator dynasties during the Jurassic period, demonstrating, once again, that extinction often clears the path for unfamiliar evolutionary successors, rather than restoring what came before. A similar convergence appears near the end of the Cretaceous period. The Deccan traps erupted across what is now India during approximately 66 million years ago, overlapping with the asteroid impact that marked one of Earth's most famous extinction boundaries. Although the impact delivered catastrophic consequences of its own, prolonged volcanic emissions likely intensified environmental disruption by releasing additional carbon dioxide into the atmosphere. Rather than acting as competing explanations, volcanism and impact may have reinforced one another, narrowing the capacity of already stressed marine ecosystems to recover before further disturbances arrived. Evidence linking these immense eruptions to marine crises extends beyond coincidence in time. Within layers of ancient seafloor sediments, scientists have examined osmium isotope ratios preserved during intervals of widespread oxygen depletion. These distinctive chemical signatures match the influence expected from large igneous province volcanism, providing a direct geochemical connection between volcanic activity and individual oceanic anoxic events. The rocks themselves preserve the sequence, recording volcanic disturbance followed by widespread changes in ocean chemistry and biological decline. Viewed together, these records reveal a remarkably consistent relationship. Whenever one of these immense volcanic provinces emerged, marine extinction rates rose dramatically. The pattern repeats across multiple geological periods, different continental arrangements, and entirely different groups of organisms. Such consistency suggests that large igneous provinces are not isolated catastrophes, but recurring expressions of Earth's internal dynamics, repeatedly activating the same interconnected vulnerability mechanisms that have reshaped marine ecosystems across hundreds of millions of years. The fossil record, therefore, preserves more than isolated disasters. It preserves the enduring rhythm of a planet whose deepest geological processes have repeatedly reached upward to transform the living ocean. The greatest structures sustaining life in the sea cannot be seen from its surface. They leave no towering outline against the horizon, no visible boundary separating one region from another. Instead, They move beneath the waves as immense rivers of water, flowing through the darkness with patient persistence. These currents form an invisible infrastructure that supports nearly every level of the marine food web. While they continue their ancient circulation, abundance flourishes. When they weaken or change course, the consequences spread across entire oceans. Among these hidden systems, the global thermohaline circulation stands as one of the most important. Driven by differences in temperature and salinity between water masses, it connects distant oceans into a single planetary network. Dense water sinks in colder regions, while lighter water rises elsewhere, creating an immense circulation that carries heat, dissolved gases, and nutrients across extraordinary distances. Though imperceptible to any individual animal, this continuous movement establishes the environmental stability upon which marine ecosystems depend. Its influence reaches upward from the greatest depths. Nutrient-rich water, resting far below the surface after countless generations of sinking organic material have accumulated within it, is gradually lifted toward shallower layers through circulation and upwelling. Once sunlight reaches these nutrients, microscopic phytoplankton multiply across the illuminated sea. These tiny drifting organisms become the first living link in an immense biological chain, nourishing zooplankton, sustaining schools of fish, supporting marine mammals, and ultimately providing the energy required by apex predators. When global warming alters the balance between warm surface water and colder deep water, this circulation begins to lose strength. Surface layers become less dense, reducing their tendency to sink and exchange with deeper waters. The contrast that drives the planetary current system weakens, and the steady upward transport of nutrients slows. Phytoplankton productivity declines as fewer essential nutrients reach the sunlit ocean. What begins as a physical change in water movement gradually becomes a biological change, extending through every level of the ecosystem. The richest hunting grounds in the sea have always reflected this invisible process. Regions where deep, nutrient-rich water rises toward the surface support extraordinary concentrations of life because energy enters the food web there in exceptional abundance. Fish gather in immense numbers, marine mammals follow seasonal migrations, and large predators establish territories where prey remains dependable. These productive upwelling zones owe their existence not to chance, but to the continual operation of ocean circulation. Should that circulation diminish, the biological richness that once characterized these waters fades with it. At greater depths, another consequence begins to emerge. Ocean stagnation develops when deep water is no longer exchanged efficiently with the surface. Fresh supplies of oxygen cease arriving, while decomposing organic matter continues consuming what remains. Gradually, the deep ocean becomes increasingly depleted of oxygen, creating conditions favorable for widespread anoxia. Thus, weakened circulation does more than reduce productivity near the surface. It also transforms the chemistry of the abyss itself, linking physical change with biological decline through a continuous chain of cause and effect. The pathways of these currents are shaped not only by climate, but also by the slow movement of continents. When tectonic forces close ancient seaways or open new ocean passages, the routes followed by major currents are fundamentally reorganized. The permanent closure of the Central American Seaway illustrates this process with remarkable clarity. As the land bridge rose between North and South America, currents that had once flowed freely between the Atlantic and Pacific Oceans were redirected. Heat transport shifted, circulation patterns evolved, and marine habitats across both oceans experienced long-lasting ecological consequences. For apex predators, these changes unfolded without visible warning. Their prey gradually abandoned familiar feeding grounds, productive regions contracted, and once reliable migration pathways altered across immense distances. No single current determined their survival, yet together these hidden movements formed the living framework supporting every hunt. The invisible infrastructure beneath the sea had changed its course, and the entire ocean slowly reorganized around its new design. Power in the ocean has never been measured by strength alone. Across immense spans of geological time, another measure gradually reveals itself, one that only becomes visible when entire ecosystems are pushed beyond their ordinary limits. At those moments, the creatures that once appeared unshakable often vanish first, while smaller and less celebrated forms of life continue onward. The fossil record preserves this contrast with remarkable consistency, revealing a paradox woven deeply into the history of marine evolution. When paleontologists compare survival across the great extinction boundaries, a recurring pattern emerges with striking regularity. Larger animals disappear more frequently than smaller ones. Ecological specialists vanish more readily than adaptable generalists. Species that produce relatively few offspring struggle far more than those capable of reproducing rapidly. These trends appear repeatedly despite the different geological events that triggered each extinction, suggesting that the biology of the organisms themselves strongly influences which lineages endure and which gradually fade from the oceans. These characteristics describe apex predators with remarkable precision. They occupy the highest position within their food webs because they have evolved extraordinary bodies, refined hunting behavior, and ecological roles shaped over millions of years. Their immense size allows them to overpower formidable prey and discourage competitors. Their specialized senses and anatomy enable remarkable efficiency within familiar environments. Their slower pace of reproduction reflects the substantial investment required for each new generation. During long intervals of environmental stability, these traits become powerful advantages, allowing dominant predators to thrive across vast marine landscapes. Yet the same qualities begin to shift from strengths into burdens as the surrounding world changes. A large body demands an equally large and dependable supply of food. Specialized hunting techniques become increasingly ineffective when customary prey declines or disappears. Long developmental periods delay the arrival of mature adults capable of replacing individuals already lost. Each biological investment that once increased success under favorable conditions becomes progressively more difficult to sustain as ecological disruption spreads through the food web. Evidence gathered from numerous extinction intervals demonstrates that body size alone carries measurable consequences during periods of crisis. Larger species consistently experience greater extinction risk than smaller ones occupying similar environments. This relationship remains one of the strongest statistical findings in paleontology because it appears across many unrelated groups of organisms rather than within a single lineage. Size provides impressive ecological influence during prosperous ages, yet it also magnifies dependence upon abundant resources, extensive habitat, and stable environmental conditions. Metabolism deepens this imbalance. Every movement of an apex predator requires energy gathered from prey that has itself drawn nourishment from many lower levels of the food chain. When productivity weakens, energy becomes increasingly difficult to obtain. A predator adapted for consuming large marine mammals or substantial fish cannot easily survive upon much smaller organisms. Its digestive system, hunting strategy, and physical design have all been refined for a particular ecological role. Evolution favors efficiency, but efficiency often narrows flexibility when circumstances begin to change. Reproduction adds another layer to this unfolding pattern. Smaller marine animals may produce enormous numbers of offspring within comparatively brief periods, allowing populations to recover after disturbance. Large apex predators follow a very different path. They mature slowly, bear relatively few young, and invest considerable resources into each one. Population losses, therefore, accumulate more rapidly than they can be replaced. Even if environmental conditions later begin to improve, too few breeding adults may remain to restore the lineage before additional pressures emerge. Seen across geological time, the ocean repeatedly favors two contrasting evolutionary strategies, each successful under different circumstances. One rewards dominance, specialization, and mastery when ecosystems remain productive and dependable. The other rewards adaptability, flexibility, and rapid renewal when instability reshapes the living world. Neither strategy is universally superior because each flourishes within its own environmental setting. The history preserved in ancient sediments reveals that the most commanding hunters were never defeated by weakness alone. Their greatest strengths carried within them the conditions of their own vulnerability whenever the ocean gradually rewrote the rules by which life endured. Survival leaves a different kind of signature than dominance. Across the immense archive of ancient seas, the creatures that endured were not always the fastest hunters or the largest bodies moving through open water. Their legacy appears instead as an unbroken thread extending through repeated moments of planetary upheaval, revealing that persistence follows principles distinct from those that create supremacy during more stable ages. Among vertebrate animals, sharks stand apart with an extraordinary record. Their lineage has survived every major mass extinction recognized in the history of complex marine life, enduring the Ordovician extinction, the Devonian extinction, the Permian extinction, the Triassic extinction, and the Cretaceous-Paleogene extinction. Entire dynasties of marine reptiles rose and disappeared. Countless fish lineages flourished before fading from the fossil record. Yet somewhere within the remarkable diversity of sharks, enough forms always remained to carry the lineage beyond each ecological crisis and into the changing oceans that followed. Their endurance was never built upon overwhelming strength alone. Instead, it emerged from diversity accumulated across roughly 450 million years of evolution. Sharks gradually expanded into an astonishing variety of ecological roles. Some became swift hunters of open water, while others settled near the seafloor. Some specialized in crushing shell-bearing animals, while others filtered tiny drifting organisms from seawater. Certain species thrived in warm tropical environments, whereas others occupied remarkably cold regions that would have challenged many marine predators. When one habitat deteriorated or one food source vanished, another branch of the lineage often continued elsewhere, sheltered by a different way of life. This flexibility transformed extinction from a single catastrophic event into a challenge distributed across many ecological strategies. A crisis capable of eliminating one specialized shark lineage did not necessarily threaten another adapted to different prey, different depths, or different temperatures. Diversity functioned as a biological form of resilience, ensuring that the disappearance of one branch did not erase the entire evolutionary tree from the ocean. Body size strengthened this resilience even further. Smaller sharks generally required less energy each day than gigantic specialists. Their prey could consist of more abundant animals occupying lower positions within the food web. They reached reproductive maturity sooner and often produced offspring at a faster pace than immense apex predators. During intervals when marine productivity weakened, these advantages became increasingly important. Populations, supported by modest energy demands, could continue through conditions that proved unsustainable for predators, dependent upon enormous quantities of large prey. Another enduring survivor illustrates this pattern through an entirely different path. The Nautilus has retained a body design that has changed remarkably little across hundreds of millions of years. Rather than relying upon speed or dominance, it occupies deeper waters where environmental conditions often remain more stable than those found near productive coastal ecosystems. Its broad diet allows it to consume whatever suitable food becomes available, while its comparatively modest metabolism reduces the amount of energy required for continued survival during prolonged periods of scarcity. These characteristics have enabled the lineage to persist through repeated episodes that reshaped much of marine life. Viewed together, these examples reveal a recurring principle extending across roughly 500 million years of ocean history. The organisms most likely to survive profound environmental disruption are rarely those perfected for a single set of favorable conditions. Instead, resilience emerges from adaptability, a capacity to tolerate changing temperatures, shifting oxygen levels, varied prey, and unfamiliar habitats provides opportunities unavailable to highly specialized competitors whose success depends upon a narrower range of circumstances. The fossil record therefore preserves more than a catalog of extinctions. It also records the qualities repeatedly favored whenever the oceans entered periods of instability. Generalism, physiological flexibility, moderate energy requirements, and ecological diversity appear again and again among the lineages that continued beyond each crisis. They remind us that the longest story in marine evolution belongs not to the animals that ruled the seas for a time, but to those capable of enduring as the seas themselves were transformed. The oldest presence in this story has never been a predator, a reef, or even the continents themselves. It has always been the ocean, carrying its own history across spans of time so immense that even the rise and disappearance of entire animal dynasties become passing chapters. Every lineage that has entered its waters has done so within a world already shaped by countless transformations, each one preparing the conditions for those that would follow. The ocean has existed for approximately 4 billion years, while complex animal life has occupied it for roughly 540 million years. Even this vast interval represents only a relatively recent portion of the ocean's existence. The succession of apex predators traced through this journey, from ancient armored hunters to marine reptiles and giant sharks, occupies only a small fraction of that already limited window. Their stories appear immense from a human perspective, yet within the ocean's deeper chronology, they resemble brief intervals carried along an endlessly changing current. Throughout that immense history, equilibrium has remained an illusion. The chemistry of seawater has shifted repeatedly. Oxygen concentrations have risen and fallen. Temperatures have alternated between warmer and cooler worlds. Patterns of circulation have strengthened, weakened, and reorganized. Each combination of these conditions favored different communities of living organisms, allowing certain lineages to flourish while gradually placing others under increasing pressure. The ocean has never remained fixed long enough for permanence to become its defining characteristic. Every geological era remembered for remarkable marine life reflects one temporary arrangement within this ongoing sequence. Coral-rich Devonian seas, the reptile-dominated waters of the Jurassic, and the whale-filled oceans inhabited by Megalodon each depended upon particular combinations of climate, chemistry, circulation, and geography. Their apparent stability lasted not because change had ceased, but because the underlying geological forces operated across timescales extending far beyond the lifespan of any individual species. Eventually, those deeper processes altered the conditions upon which each biological world depended, opening opportunities for new communities while closing them for others. Some of these influences arise from the restless interior of the planet, where tectonic movement gradually reshapes continents, redirects currents, and creates new ocean basins. Others originate far beyond Earth's surface. Periodic variations in the planet's orbit around the Sun and subtle changes in the angle of its rotational axis alter the amount and distribution of solar energy reaching different regions. These repeating astronomical rhythms unfold across intervals ranging from approximately 20,000 years to 100,000 years. Layered upon slower volcanic and tectonic processes, they create recurring patterns of climatic change that the geological record associates with repeated shifts in ocean circulation, oxygen distribution, and episodes of widespread ecological stress. No single cycle determines the fate of marine ecosystems by itself. Instead, these influences overlap, reinforce, or counterbalance one another across immense spans of time. The resulting ocean is not a static environment interrupted occasionally by catastrophe. It is a continuously evolving system whose biological communities respond to physical and chemical conditions that are themselves always in motion. Even intervals remembered as unusually stable contain gradual transformations unfolding beneath the surface, almost imperceptible within the lifetime of any organism living through them. Seen from this broader perspective, extinction and renewal become parts of the same enduring process rather than opposing events. As one configuration of the ocean slowly gives way to another, familiar ecological relationships dissolve while different ones emerge. New opportunities appear where older foundations disappear, and evolutionary pathways branch in directions that could never have existed under previous conditions. The ocean remains the constant presence through every transition, not because it resists change, but because change has always been its defining nature. The seas surrounding the continents today, therefore, represent neither the beginning nor the conclusion of Earth's marine story. They are simply another temporary expression of an ancient system whose transformation continues without a final destination. An empty ocean has never remained empty for long. Across the immense chronology of Earth's seas, each disappearance has opened room for unfamiliar possibilities, allowing forms of life that once existed only at the margins to expand into roles that had previously been occupied by others. The history preserved in ancient sediments therefore records not only endings, but continual transformation as one living world gradually gives way to another. For the organisms experiencing a mass extinction, the event itself was an overwhelming biological catastrophe. Entire food webs unraveled within comparatively brief geological intervals, and countless lineages disappeared forever. Yet, viewed across millions of years rather than individual lifetimes, those same intervals became turning points that reshaped the direction of evolution. Ecological space that had remained occupied through prolonged periods of stability suddenly became available, allowing surviving groups to diversify in ways that had previously been impossible. After the Permian extinction erased approximately 96% of marine species, the oceans entered a profoundly altered state. The communities that emerged were not restored versions of those that had vanished. Instead, the Triassic seas gradually filled with unfamiliar combinations of animals possessing different body designs, different feeding strategies, and entirely new ecological relationships. Predator lineages that would later dominate the oceans arose within environments fundamentally unlike those that had existed before the extinction. Their success depended not upon restoring the lost Permian world, but upon adapting to conditions created by its disappearance. The same pattern appeared again much later when major marine reptile groups declined during the middle of the Cretaceous. As pliosaurs and ichthyosaurs retreated from their former dominance, ecological opportunities expanded for other hunters. Mosasaurs diversified into remarkable forms, while shark lineages continued exploring new ecological roles across changing marine environments. The predators familiar from later chapters of Earth's history inherited opportunities created by extinctions that occurred long before their own success. Their rise was not independent of those losses, but deeply connected to them. Even among relatively recent events, this recurring transformation remains visible. After the extinction of Megalodon, approximately 3.6 million years ago, the oceans did not leave the ecological space associated with gigantic marine consumers permanently unoccupied. Instead, another lineage expanded into extraordinary body sizes through an entirely different strategy. Baleen whales, including the blue whale, the fin whale, and the humpback whale, diversified within marine ecosystems, no longer shaped by the presence of the immense shark that had once hunted large whales. These giants achieved greatness not through predation, but through filtering immense quantities of tiny organisms from productive waters, illustrating that similar scales of life can emerge through profoundly different evolutionary paths. This recurring pattern reveals that extinction is not merely the removal of species from an ecosystem. It also releases biological opportunities that had previously remained constrained by established ecological relationships. Habitats become available. Food resources acquire new importance. Evolutionary experiments, once limited by intense competition, begin expanding into directions that earlier conditions had prevented. The ocean continually reorganizes itself around whatever organisms remain capable of responding to its changing circumstances. Such transformation should not be mistaken for progress toward any predetermined destination. The fossil record offers little support for a steady movement toward greater complexity or increasing diversity alone. Instead, it presents a succession of biological configurations, each shaped by particular combinations of climate, chemistry, geography, and evolution. Every stable interval eventually gives way to another arrangement built from the survivors of preceding change, carrying forward some ancient lineages while introducing entirely new ones. Seen across the full sweep of geological time, the ocean resembles an ever-changing mosaic rather than a single continuous ascent. Every dominant community eventually becomes part of the foundation upon which another is built. The great predators, whose stories have unfolded through these ancient waters, did not simply disappear into absence. Their passing altered the shape of the living world, making possible ecosystems that could never have existed while the previous order still endured. In that enduring cycle of loss and renewal, the ocean continually reshapes itself without repeating exactly the world that came before. Long before any observer could measure the chemistry of seawater or trace the movement of deep currents, the ocean itself had already preserved a record of recurring change. Layer after layer of ancient sediment reveals that the same physical processes have returned across immense spans of geological time, each unfolding under different circumstances, yet following familiar pathways. The forces that reshaped prehistoric oceans have never belonged solely to the distant past. They remain part of the planet's living system, observable today through careful measurement and continued scientific study. Among the clearest of these processes is the increasing concentration of carbon dioxide within the atmosphere. During ancient episodes of intense volcanism, enormous quantities of carbon dioxide entered the air over extended intervals, gradually altering both climate and ocean chemistry. Today, the source differs, arising primarily from human activity rather than volcanic eruptions, yet the chemistry that follows remains governed by the same physical laws. The ocean absorbs approximately 1/4 of the carbon dioxide released into the atmosphere, where it reacts with seawater and alters the balance of carbonate compounds that countless marine organisms rely upon to build shells and skeletons. These chemical changes have been measured directly across the modern ocean and demonstrate a continuing pattern of surface water acidification. At the same time, another process recognized throughout the fossil record is becoming increasingly apparent. As seawater grows warmer, its capacity to retain dissolved oxygen gradually declines. Marine organisms continue consuming oxygen while organic material continues decomposing beneath the surface, placing additional demands upon an already diminishing supply. Across recent decades, researchers have documented the expansion of regions where oxygen concentrations have fallen well below historical levels. These developing areas of reduced oxygen differ greatly from the immense prehistoric episodes that transformed entire ocean basins, yet they arise through the same underlying physical relationship between temperature, circulation, and dissolved gases. Ocean circulation also remains central to this unfolding picture. The vast system of interconnected currents that transports heat, nutrients, and oxygen across the globe depends upon differences in water temperature and salinity. Oceanographers have measured signs that the Atlantic meridional overturning circulation, the present expression of the broader thermohaline circulation, has weakened compared with earlier conditions. Because this circulation helps distribute nutrient-rich waters throughout marine ecosystems, continued observation has become an important focus of scientific research. Even modest changes may influence biological productivity in regions where countless marine species depend upon the continual renewal of surface waters. None of these observations should be understood as a direct repetition of any single prehistoric extinction. The Earth of today differs profoundly from the worlds that surrounded the Permian, the Triassic, the Cretaceous, or the Miocene. Continents occupy different positions. Ocean gateways have changed. Living communities have evolved, and the timescales involved are not identical. Science, therefore, avoids declaring that one period will inevitably mirror another. Instead, it recognizes that similar physical mechanisms can operate under different circumstances while producing outcomes shaped by the particular conditions of each era. This distinction gives the fossil record its enduring value. Ancient oceans function as an immense archive of natural experiments extending across hundreds of millions of years. They demonstrate how warming influences dissolved oxygen, how changing chemistry affects marine organisms, how circulation governs biological productivity, and how these interacting processes reshape entire ecosystems when they converge over sufficient time. The record does not provide certainty about the future, yet it offers an extraordinary catalog of relationships repeatedly observed across Earth's history. Within that immense archive, one pattern appears with remarkable consistency. Apex marine predators flourish when the foundations supporting ocean life remain productive and interconnected. As those foundations become disrupted through changing chemistry, declining oxygen, altered circulation, or shifting food webs, the effects gradually rise through every ecological level. Paleontology cannot forecast the precise course of the modern ocean, but it can illuminate what these mechanisms have accomplished before preserving in stone a detailed account of how the living sea responds whenever its deepest systems begin to change. There comes a point along the geological timeline when individual ages begin to merge into something larger. Distances once measured in millions of years become neighboring moments, and the succession of oceans resembles the changing light across a single landscape. From that elevation of time, the rise and disappearance of every great marine hunter no longer appears as isolated drama. Instead, each belongs to one uninterrupted process that has unfolded since the earliest seas settled across the surface of the earth. Within that immense continuity, dominance loses the permanence it seems to possess from the viewpoint of a single era. Every apex predator occupied its place because the surrounding ocean happened to provide the exact combination of temperature, chemistry, circulation, and living abundance required for its way of life. Its strength emerged from harmony with those conditions rather than mastery over them. The immense jaws, powerful muscles, refined senses, and specialized methods of hunting that defined each ruling lineage were expressions of an environment that temporarily favored those qualities. As the environment changed, the same adaptations that once represented extraordinary success gradually became less suited to the world unfolding around them. The armored form of Dunkleosteus flourished within seas, unlike any that followed. The immense pliosaurs crossed waters shaped by another arrangement of continents, currents, and marine communities. Megalodon patrolled an ocean whose productive coastlines, abundant prey, and suitable nursery grounds existed only during a particular chapter of Earth's history. None of these rulers vanished because a greater predator arrived to overthrow them. Their decline began when the ocean itself altered the conditions that had once allowed them to thrive. Geological change reached farther than teeth or speed could ever extend, quietly reshaping the foundations beneath every food web until even the most accomplished hunters found themselves living within a different world. Seen across billions of years, the ocean has never belonged to any creature that entered its waters. It has welcomed countless forms of life, each suited to a temporary arrangement of physical forces that eventually yielded to another. Continents drifted apart and later approached again. Deep currents shifted their paths. The chemistry of seawater transformed. Oxygen rose and fell. Climates warmed and cooled, and biological communities reorganized themselves in response. Through every transition, the ocean neither preserved familiar lineages nor favored new ones. It simply continued responding to the forces acting upon the planet, opening opportunities as older possibilities gradually faded. This broader perspective softens the apparent finality of extinction without diminishing its reality. For the animals that lived through each transition, those moments represented profound biological loss. Yet over spans that stretch beyond ordinary imagination, each ending also became part of an ongoing reshaping that allowed different communities to emerge from changing circumstances. The living ocean was never frozen into a single successful design. It remained an evolving system whose patterns reflected continual adjustment rather than lasting completion. From within a human lifetime, dominance appears absolute and disappearance appears permanent. Geological time reveals both to be temporary conditions, lasting only as long as the surrounding world continues to support them. Every flourishing lineage occupies a brief interval between older configurations and those still waiting to unfold. The ocean carries each of them for a time before continuing onward, unchanged in its deeper rhythm, even as every visible inhabitant changes upon its surface and within its depths. Across the vast history traced through these ancient waters, the greatest constant has never been any predator, any lineage, or any single age of life. It has been the ocean itself, endlessly reshaping the conditions of existence, carrying every dynasty for a while, then continuing its immense journey without pause, without possession, and without any final destination. Every age of the ocean has existed within a span of conditions that could never last forever. Each great predator rose during a rare alignment of temperature, circulation, chemistry, and abundant prey, a combination assembled over immense stretches of geological time and sustained only until the planet itself continued its slow transformation. Those intervals appeared enduring to every creature living within them, yet the fossil record reveals them as passing chapters. The ocean opened each window gradually, filled it with extraordinary life, then closed it with the same patient rhythm that had created it. Nothing in that rhythm has truly ceased. Deep beneath the continents and ocean floor, molten rock continues its movement. The continents themselves continue drifting across the surface of the Earth. Variations in the planet's orbit and the angle of its axis continue shaping cycles of warming and cooling across spans that far exceed recorded history. The chemistry of the sea continues responding to every change in atmosphere, every alteration in circulation, and every shift in the balance between living organisms and their environment. These forces have accompanied complex marine life since its earliest appearance, remaining constant companions even as the inhabitants of the ocean have changed beyond recognition. There is now an additional influence unlike any preserved within older chapters of the geological record. For the first time since complex life emerged, one species has become capable of altering atmospheric chemistry, reshaping coastlines, transforming habitats, and influencing the functioning of planetary systems on a global scale. Humanity did not replace the ancient geological engines that have always governed the ocean. Instead, it has become another force acting alongside them, operating within the same interconnected system whose history extends across billions of years. Viewed through that wider perspective, the disappearance of prehistoric apex predators is not a catalog of biological failure. It is evidence of the immense scale upon which the ocean operates. Conditions capable of supporting one dynasty eventually yielded to conditions favoring another, not because the earlier creatures lacked strength or refinement, but because the foundations beneath their existence gradually transformed. Geological time measures those transitions as relatively brief episodes, although each extended far beyond the duration of any civilization that has ever existed. The rulers of those vanished seas remain no less remarkable because they disappeared. Dunkleosteus belonged completely to the world that produced it. The great pliosaurs reflected another ocean shaped by different continents and different currents. Megalodon represented the culmination of conditions that favored immense predatory sharks until those conditions slowly faded. Each animal became the fullest expression of what the living ocean could create during its own particular moment, just as the marine life surrounding us today reflects the circumstances of the present age. Throughout every transformation, the ocean itself has remained the enduring thread. It has continually rearranged energy, nutrients, chemistry, circulation, and life into new patterns without ever arriving at a permanent destination. Every ending released possibilities that earlier worlds could never have supported. Every beginning emerged from foundations laid by oceans that no longer existed. Across billions of years, this continuous exchange has produced astonishing diversity without ever repeating exactly the same living world. The story traced through these ancient waters, therefore, reaches beyond the disappearance of any single predator or lineage. It becomes the story of an ocean that has never stopped becoming something new. Long before eyes evolved to witness its surface, It was already shaping the conditions from which life would emerge. Long after every creature alive today has passed into the geological record, it will continue responding to the same immense forces that have guided it from the beginning. The prehistoric giants were one chapter within that history, the living ocean another, and the greater narrative continues to unfold beneath the tides, carried forward by a planet whose oldest storyteller has always been the sea itself.